Good afternoon, good evening. Thank you all for joining us tonight for another session of Through the Lens. My name is Joshua Stewart. I am the Senior Associate Director for our UVA Clubs Global Networks. Through the Lens is a virtual faculty lecture series highlighting faculty from across grounds whose research and knowledge promote intellectual discourse. Enjoy these riveting topics from the comfort of your own home and learn like our current who's as we bring professors to you. I would like to say that closed captioning is available at the bottom of your screen. And without further ado, I would like to introduce our speaker today. And before I do that, I do want to acknowledge that it is Holy Thursday or Maundy Thursday. So for those who are joining us or participating in that, thank you for doing so. Now to our introduction. Professor Dick Lindgren started physics research in sound and vibration studies on submarines at General Dynamics in 2 summers while an undergrad at URI. Upon entering graduate school, he carried out studies in magnetism in iron and liquid helium temperatures, earning a master's degree in 1964 from Wesleyan University. And then he earned a PhD in 1969 from Yale University in nuclear physics studies using the first operational Emperor tandem Van de Graaff accelerator. Eventually, he found his home as a research professor of physics at UVA in 1985. Professor Lindgren expanded nuclear studies with the NSF-supported grant to include proton and pion scattering on nuclei to complement his electron scattering work, and gradually moved to higher electron scattering studies at the new high-energy 4GV lab in Newport News, now known as the Jefferson Lab. Lindgren was also a PI of the first NSF-sponsored MRI grant to complement existing detector instrumentation in Hall A. At UVA, he also directed the NSF Research Experience for undergraduate programs for 10 years and co-founded and was the first director for 10 years of the Masters of Arts in Science and Physics Education degree program, which he graduated over 150 high school physics teachers. Incredible. He advised all the students and taught more than half the physics courses. He has taught and organized many STEM summer workshops for over 20 years with annual support from the State Council of Higher Education in Virginia. Lindgren has also published and co-published hundreds of articles in nuclear physics and given many professional talks in research, teaching, and education. Although presently retired as Emeritus Research Professor in Physics, Professor Lindgren teaches a few courses a year, including physics of sports, which we'll be learning about today, and is a trial course, which started as a trial course in the summer session in 2020. He still teaches it twice a year. And in his spare time, he continues to improve his tennis skills. So we'll hear a little bit about that, and hangs out with his family. Without further ado, thank you for joining us, Professor Lindgren.
Thank you very much for that elaborate invitation to speak to you. Thank you very much for inviting me. And I'm going to talk to you about physics of sports and probably start out with a little bit in baseball, and then we'll go on to basketball, where I plan to emphasize most of the material. I'd like to acknowledge a few people that have helped me get through this work. One is Dr. Al Tobias, our lab demonstrator. Anthony, who made a video of his 3-throw available. Ying Lindgren helped with the video setups, and hundreds of students who took the course that really got me motivated to do all this work. So let's start off. By no means do I imply throughout this talk you can be a great athlete by just studying physics. That's the first thing somebody always asks me. Oh, you need to study physics to be an athlete. In fact, the opposite is true. You know, you can be a great athlete without studying physics. You don't have to learn about vector analysis, or you don't have to calculate anything before you do it. You just do it. Perhaps, however, you can learn a little bit faster if you know a little bit about what you're doing in terms of the science, and maybe after you become really good, you can fine-tune your craft by knowing a little bit about the physics. And if you coach, it might help you coach more efficiently and teach more efficiently. So I'm going to make a few comments about my physics of sport course as we go along. And then basically, I'm going to discuss a bunch of rules. I call them rules to help understand the motion of sport balls. But basically, I'm just trying to sneak a little physics in there. They're really going to be forces. One force will be gravitation, one will be the drag force, and then the so-called Magnus force, named after Gustav Magnus, who studied the spins of cannonballs in cannons in the 1800s. I'll show some demonstrations to help explain how drag forces limit the ball's distance and how the Magnus force extends their distance and causes balls to curve. And then we're going to talk about how to shoot a basketball and maximize your margin of error to make nothing but net. Well, I skipped my team. Here's my team. I've been practicing for 60 years and I'm still on the JV team. Here's my instructor here and the rest of our TAs. So let's go practice. So about my course, yes. Number of things we cover: center of mass, okay? Utilizing the center of mass to maximize the high jump, maximize how far you can do the broad jump. Where on the baseball bat should you hit the ball? Where is the sweet spot? We talk about center of mass, center of percussion, vibrations and nodes and so on. So that all sounds like physics. In basketball, for example, we talk about hang time. So we spend a lot of time on that. Talk about how to follow through in tennis. The lone man wins in football. What's the banana curve in soccer? Well, and the list goes on. How about a float serve in volleyball? Why is this like a knuckleball? All right, and then a number of athletes have taken our courses, and in particular, I've listed the basketball players on the far left here, and some of them you recognize. The present team, the championship team, including a few other players. This is over the last couple of years. All right, we'll just move on from there, and we're going to start with a home run. So let me just show you one little quick video here. Let's let it play for a minute.
Stanton drills it deep left field like a rocket. Up into the seats it goes. That's 20 rows up in the deepest part of the park, and Stanton has untied this game.
All right, let me just stop it there. That home run that he hit went 504 feet. No, that is a Guinness World Record for a home run, as well as a major league record. The question is, why hasn't anybody else hit one that far? And let's ask where he hit it. It turns out he hit that at Coors Field in Denver, Colorado. And so I have a question really to stop right off here, just to get you thinking about it. Why would it be possible to hit the longest home run in Coors Field, Colorado? What is different about Coors Field than any other park? Well, just think about it a few minutes, and you realize that it's a mile high. And if it's a mile high, that means it has a less dense atmosphere. In fact, the density of the air is 18% less than, let's say, Fenway Park in Boston, or Yankee Stadium, or most of the parks. And you can certainly hit the ball farther when the atmosphere is less dense. Density plays a big role, all right, in putting a force of drag on the ball, preventing it from going as far. So let me just skip this and start right off with the forces that act on a baseball when it's hit by the batter. And here we can see the ball, we can see the bat, and there's a huge force that gets that ball started. Several hundred pounds, probably close to 1,000. All right, so the ball goes up in the air, and what's the Final Four? Yes, this is basketball season, so we talk about the Final Four. In this case, we have 4 forces. One force, let's say, is gravity. Now, you all know what gravity is. It acts downward. Well, when the ball goes up in the air, the acceleration of gravity to slow that ball down in the vertical direction in the English system is 32 feet per second per second. But not only does that drag it down to the ground, the drag force, you see this little blue vector here, is in the opposite direction than this dotted red arrow, which is the velocity of the ball. The drag force always acts in the exact opposite of the direction that the ball is moving. That's the second largest force. The next is the Magnus force, which gives rise to a lift force, which is this little red vector here, which is always perpendicular to the direction of the ball is going. And that gives a lift to the ball depending on the orientation of the spin. In this case, you have what we call backspin. As you look in the direction that the ball is going, you see that the spin is coming backwards. So we call it backspin. And that gives lift to the ball while it's on the way up. There's one more force that's not very important in terms of baseballs, but in terms of basketball, it's a little more important, and that's buoyancy. The buoyant force is nothing more than a force that opposes gravity by a small amount. So that helps a little bit. Now, as an analogy to the buoyant force, of course, that's the force you feel in water, all right, when you're, say, floating or even when you're submerging. You weigh less in water due to the buoyant force. Well, there's also a buoyant force in the air, because air is a fluid. All right, it's in it. So in the air, the density of it is a lot less than the density of water, so the buoyant force is a lot smaller, but nevertheless, it exists. Usually, I'll represent it by a very small arrow, and we're going to neglect it in most of the situations. So here's a picture of a flight of a baseball hit at 100 miles an hour at a launch angle off the bat of 30 degrees. And with only gravity acting, you see, it goes almost 600 feet. Now, a few minutes ago, I said 504 feet was actually, that is the world record. Well, that was held but the density is less, but there is no density at all. You will get typically baseballs hit 600 feet, but you know that in most stadiums, they average around 400 feet. So this is not the whole story, but this just simply will get you set an example for what the maximum would be. And you see this very nice parabolic curve, okay? Now, suppose we input the drag. So now I add the drag force on, which is going to be the blue. So now we've got gravity plus drag acting. And oh my gosh, you can see what's happened in the blue curve. All right, it's a lot smaller. The ball doesn't go as high here, and it doesn't go as far. It's only about 300 feet. So something must be missing, right? Because we know balls go at least 400 feet on average. Well, this drag force is sort of a pain in the neck, as you can see. And here's a golf ball. And you can see with the golf ball is moving to the left, it has to push all these molecules of the air out of the way. And pushing them out of the way, it takes energy. So what will happen, that energy gets sapped from the kinetic energy of the ball. Just quickly mentioning here, the drag force is given by a formula, yes, by some coefficient, which is taken from experiment, all right, some number times the density of air times the cross-sectional area of the ball. That is, the larger the ball, the more the drag, the larger the density, the more the drag. Then the key thing here is proportional to the velocity squared. So if you double the velocity, you're gonna like, what's happened is the drag force is going to be 2 squared, or 2 times 2 is 4, will be 4 times greater. So when this ball is going 100 miles an hour, it's going to have a huge drag force. And that's why it only goes roughly half the distance. Well, if we add in the Magnus force, now when you hit a ball, if we add a little spin to it. Now, the Magnus force doesn't work unless the ball is spinning. So if we have a little backspin to this ball, and you add that into the drag and the gravitational force, you get the red curve. And now you see the red curve adds lift, and it adds back, all right, some positive energy in order to get the final trajectory of the baseball. And you will see that this force is proportional also to the density of the air. It's also proportional to the cross-sectional area of the ball as well, but when you factor in everything, it turns out to be proportional to the radius cubed. So it gets really big as you increase the radius. And I'll show you a demo a little bit later on that. And then it's proportional to the velocity times F. F is the rate of rotation of the ball spinning. Usually in terms of rotations per minute, it can be as high as 1,800 rotations per minute. In terms of hertz or rotations per second, that's around 30, so about 30. All right, so the ball must be spinning. So when you hit that ball off the bat, you want to get that backspin acting on the ball. All right. Now, there's something else very interesting about this that I have to point out to you, and that's called the drag crisis. That's a very interesting concept that I'd like to talk about for a few minutes, because we want to be able to handle all these balls. We want to take a ball the ping pong ball, which is very smooth, a golf ball that has dimples, a tennis ball that has fur on it, a baseball that has stitches, and so on, and a basketball that has seams. We want to handle all these balls with the same forces that I just gave you. And that's where this drag coefficient comes in, this factor that's out in front. Well, it turns out that factor, you see, is very velocity dependent. It depends on what it is. And in fact, if you have a smooth ball, like a ping pong ball, which is nice and smooth, you see you have a large inhibition, a very large drag force. And you see this number is relatively large, all the way out to 140, 160 miles an hour. Kind of useless out here for most of our sport balls. So if we have a drag coefficient on a baseball or a golf ball that's so large, the balls would never go even 400 feet. But it turns out that if you rough up the ball, like if you take a golf ball and you put little dimples in it, this coefficient drops down. And that's what's called the drag crisis. When this dimpled ball, when it was discovered, if you rough up the ball, it doesn't really matter how you rough it up, you just rough it up, and you'll see this coefficient drops suddenly at some crucial speed. So this is more or less the operable drag coefficient for a baseball. I'm sorry, for a golf ball. For the baseball, which has stitches, that acts kind of like the dimples, but it's not so uniform as a dimple ball is. They kind of, as you see them here, so when the ball is spinning, you get some average effect, and this becomes the change in the drag coefficient for baseballs. And that makes life very difficult in trying to do data analytics for baseball. And then a rough ball in general, like say a tennis ball, is somewhere in the middle, or a basketball where it drops down at this point. And then depending on the details, this curve, the drag coefficient can be somewhere in between. And in order to get that, you cannot calculate that, you have to get it from experiment. All right, so I pretty much explained what's happened here. Why do golf balls have dimples? But I want to explain just a little bit more in terms of how the air is flowing around the ball. So you need a picture rather than just formulas. So here we have, let's say, a smooth ball flowing to the right at 20 miles an hour. Now, if the ball is going to the right, you can actually imagine the airflow going, I'm sorry, I think I said that wrong. The ball is moving to the left, but the airflow is moving to the right. So you can think of it either way. So as a smooth ball goes to the left, the air goes around the ball in laminar flow. As you can see, these kind of lines are laminar flow, nice and smooth, like slow moving water through a stream. But the minute it goes far around the ball, it departs from the ball. It deviates from the ball. It leaves it, and then it leaves a big wake behind it of turbulence. And when that happens, the pressure behind here is actually lower than it is in front of the ball. And so what happens, the ball kind of gets sucked back and you have a lot of drag. It's lower pressure, more drag when you have a large wake like this. If you put dimples on the smooth ball, you rough up the surface, then say that happens at about 60 miles an hour. Let's just take a number from that drag crisis curve. You will now see this, the laminar flow line actually goes further around the ball and then leaves it on the top and sort of symmetric, and it does it on the bottoms. This very small red line is called the boundary layer. It's about 1 millimeter of air between the ball and the laminar flow line. All right, and then this air mixes with this turbulence back here and allows this air to stick to the ball longer before it leaves the surface. And when it does, you now have a small wake. When you get a smaller wake, you have higher pressure back here and you get less drag. And so the whole idea then is to rough up our balls a little bit so the golfers can hit their balls further and make them happy. All right, there's a lot more going on here, but I'm not going to go into it. All I want you to see here is that a smooth ball has a large pressure area and a small ball, small wake has less drag and it has higher pressure. You also know in cycling that when you ride behind somebody else that he actually sucks you along, right? You know there's a kind of lower pressure behind a moving object due to the way the air flows. Just to give you a little idea now about how this drag affects things in Newton's law about gravity, first discovered by Galileo, that all things fall at the same rate. And that's the gravitational force, basically. Everything falls at a rate of 32 feet per second per second. So let's test this out. But you all know that if you have a feather and let's say a stone in the atmosphere, in the air, well, if you have it in a tube like this, just so that you can visualize it, the air will float down, okay, and the stone will come first. So the drag force on the air is huge. Let's pump out the air in this tube and let's see if Galileo's law is correct and they both fall at the same time. So instead of using these tubes, I'm going to use a plastic box so you can look inside, and we can use a much larger feather and you can see what happens. So here we go. All right, so here's our large feather, and I'm going to use a metal cube here, and we're going to drop them together, and let's see what happens. All right, let's start up the video. I'll just talk along as this person is demonstrating the video. So here's our plastic box, and up on top, you see the metal cube and the feather. They're held in place by a magnet on the other side. And now we're going to release them, and you'll see in air, here's the pressure in air is measured by this gauge here, and you see that the feather came down really slow, like, right? There's lots of drag on the feather. Now we're going to pump the air out. We put the feather in the metal back up again, seal it to the top, held by magnetically. We release the magnet. Here we see there's no pressure and they fall at the same time. Great. So Galileo's law holds, things fall at the same rate if there's no air in the room. Again, just to show you the comparison between the two of them, there you go. And one more showing in real time. That was in slow motion. In real time, you see how fast the feather really falls. Here we go. Come on, there we go. All right, so you got the picture. Okay, one more quick little demo. Now I'm turning on to the Magnus force. We're leaving the let's see. Yeah. Okay. We're starting with the Magnus force, and we'll show you what happens here. Now, this is kind of tricky. What I got here is a cylindrical object, a paper tube, and we're going to roll it down an inclined plane. Now, this is a very light piece of paper, and so because it is so light, and the Magnus force is very weak. And so in order to get something to accelerate and in order to visualize it, you need something that has a very low mass. I'll also show you what a Coke can does. It has more mass, and you'll see the Coke can will more or less follow this black line. But when I put the paper tube and roll it down, as it rolls down, it's going to gather spin as it rolls. When it falls off the inclined plane, All right. Is it going to follow the red line or will it follow the black line? If there's a reasonable magnetic force acting on it, Magnus force acting on it, all right, that force will be perpendicular to the direction of the tube, which is going this way. So that force will act to the left. Therefore, it's possible to expect that the paper tube will fall underneath the inclined plane. All right, so let's try it. All right, there's the, as you saw, there's the paper incline. This is our inclined plane. I held it in place. I pull the stick out, it rolls down, and you'll see it does not fall under the table at all. It just goes straight and lands on the floor. Okay. All right. Now we'll put the paper tube up there. The paper tube looks something like this, if you can see it. All right. It's a big old paper tube, kind of flimsy, but that's what you have to use in order to see this effect. You need something low mass, and here we go. There we go. See that? Right under the table. I can back it up, and you see it kind of curves right underneath there. One more time. Let it roll down there. There we go. So that's the Magnus force acting perpendicular to its original direction. And you see it makes the trajectory in it kind of like a curve. All right. I see the time is going by rather quickly here. Now, in order to see how the air is flowing behind, this is like behind across the cylinder. I've got a little demo here. This is a tube, okay? You're looking right through it, or a cylinder, and what you're seeing is air flowing past it. This is in a wind tunnel, and this is like smoke, okay? It could be water vapor, but I think this one is smoke. And it's moving across the cylinder, and behind it is the wake. This is the wake I talked about earlier that I showed you the cartoon, but this is a photograph of real air with smoke in it flowing past. And here's the huge wake, and you see where the laminar flow line departs from it, forming this thing. Let's see what happens if we add spin to the moving tube. The minute it starts to spin, I'll do it again. All right, there it goes, spinning. The air is forced to the right. All right, so let me stop it there. So we took a photograph, right, of it spinning, and what you see now is the air. The minute we put spin acting on the cylinder, it grabbed the air and moved it to the right. As you see, it's directed up in the right-hand direction. What actually happens is the air actually sticks to the tube and it's kind of dragged across it, pretty much like friction. And you all know what friction is. So it drags the air along because it's spinning this way, right? As it spins this way, it drags the air with it. And now we have an asymmetry in the air flowing around the tube. In effect, what happens is that you're going to get an asymmetry in the pressure. You actually end up with higher pressure on the right, lower pressure on the left. But the other way of looking at this, as the air is moving in this direction, it pushes against the tube, and that goes in the opposite direction. That's like Newton's third law, which says that every action is an opposite and equal reaction. So when the air pushes against the tube and the air goes this way, it pushes on the cylinder and it moves in the opposite direction to the lower left. Of course, that's a vector going this way, so you divide that, you can look at it as part of it moving directly horizontally and the other part in the direction of the air that it's coming from. But basically, it's a force that wants to move the cylinder to the left. All right, this is the last demo, and then we'll go on to basketball. All right, so now that was a cylinder. Now we're going to look at the Magnus force acting on a spherical object. So what we're going to do here, we're going to optimize the situation to get the maximum Magnus force we can. So we're going to use a 24-inch beach ball. The beach ball is pretty light, but it has a very large radius. Half of 24 inches is 12 inches. So that's pretty large. So what we're going to do is drop it off a tall building, now hall at UVA. When we drop it down, gravity will be pulling it down with its 32 feet per second acceleration. And we're going to spin it this way. We're going to hit at a given frequency. So it's going to spin at some frequency. It's going to be around 2 or 3 hertz. I will spin it in this direction. Drag will be acting upwards against gravity. There is a buoyant force, which is quite large here because it's a lot of air in there. And my rule tells me if I look at the way the ball is spinning, and if it's going this way, I look at this point right here, and the direction of the spin, whatever that is going to be the direction of the Magnus force. So that's going to be to the right. All right. And here's the strength of the Magnus force, as I said, proportional to R cubed. So that's going to give us a big effect. All right. So let's get started. All right. Here's the building we're going to be dropping it off. All right, we let that go. All right, so it's the video is started here. All right, just showing you the background. Now I'm kind of a little scared of heights here. I'm a little nervous, but I'm doing this for the benefit of science, so I'll persevere. Holding it over, now I'm going to put backspin on it and let it go. There's the backspin. There was a little horizontal velocity there, but that subsided real quick. There's the track of the ball, and you see it's going far to the right. So the Magnus force is pushing it. Now it reaches its terminal velocity really quick. So you don't get a curve here. You get more or less a straight line because the terminal velocity is fixed, and so is the Magnus force. Now, if you don't believe that, I'll now show you what happens with the ball not spinning. So now we turn the ball frequency off and let it drop without spin. And let's look what happens. Here we go. No spin. There it drops straight down. Okay. And in fact, it curved in because it did develop a little top spin in that case. If I had put top spin on it, it would have curved into the building, but I put backspin on it, so it curved away from the building. All right. And here's my calculation here of fitting it. So I did a full 4-force calculation, and as the beach ball falls, my red curve, all right, shows you the track of the ball and where it lands, and it predicted exactly the same spot where it landed. Now, to get that to work out, I had to more or less alter I don't really know what the spin was. I actually could see the different colors moving, and it was somewhere between like 2.8 and 3.4. So I averaged it and took 3.2. And I'm using a coefficient, all right, drag coefficient of 0.4. The drag coefficient of a beach ball is not known very well. It seems to vary between 0.5 and 0.2, according to people who did this kind of work. So you actually have to do it from experiment. Maybe it's 0.4 because it certainly fits our data. And if I put F equal to 0, this is what the theory predicts for the 4-force model. All right. Now on to basketball. All right, so now we know all about the Magnus force. We know all about the drag force. So how do these things affect us in basketball? Now I have to set up the diagram here for you. We need to know what launch velocity means and what launch angles mean. So here I got, this is roughly a player at the foul line. The foul line, or free throw line, is 13.9 feet from the center of the basket. Not 15, not 12, not 14, 13.9. Basket is obviously 10 feet high. Decibel, that's the launch velocity, and this is the launch angle. I won't talk much about the approach velocity or the approach angle, but that's how they're defined. And you need these kind of 4 ideas in order to understand what's going on. Now the ball is 9.4 inches in diameter. The ring is 18 inches in inside diameter. All right. You've got 8.6 inches to clear the rim with your basketball. So that's about, if you hit it in the middle, that gives you 4.3 inches in wiggle room on each side of the basket center. So you've got to be really good and know what you're doing to put that ball in the center, or to make nothing but net. So here's just a little picture of it. So when the ball comes down straight, you see the full area of the basket. But if it comes in an area like this at 45 degrees, then your wiggle room is only 2 inches. If you drop it in, you get 4.3. If you come in at 45, your wiggle room is 2 inches on each side. Factor of 2 is smaller. But then if you drop it in at 60 degrees, you get an acceptable value about 3.5 inches on each side. Now, it requires more energy to give the ball more velocity, but you have to give it more velocity when you give it more arc. However, you have the advantage of getting a greater area to drop it in the basket. What do the pros do? I'll tell you later. All right, so what are the important forces going on here? So here's my full force calculation. In this case here, it's a 25-footer, or close to a 3-pointer. So I got just like I did with the baseball, I've done you a calculation here just with gravity, and that's the black line. If I include buoyancy, that's the dash line up here. So buoyancy adds a little bit of lift, okay? That's good. It adds about a few inches. And here, if I add buoyancy and drag, what happened, and gravity, if I add this all in, now I get this dash line. So drag pulls you all the way back to here. Now, if I add the spin in and I get the full force, including the Magnus force, I put the ball right through the center. So you can see of all the forces involved, it's the drag force again that's most important in this case. But the other forces are there, and drag it, and you have to be aware of them. Let's put it that way. For this 3-pointer, you see that the discrepancy between the full force and the buoyant force is 5 inches. So that's a good size difference for a 3-pointer, but it's roughly half that for a 3-throw. Now I have one of the players in my class shooting a 3 as a special project. He took a video of himself shooting a 3-throw. So let's see what he did. And then we made a little clip and tracked the ball. So now what we can do is determine the distance the ball is from the floor. In fact, what I really do is determine where he released it from the data, and then we measure the position of the ball at each point as it moves along the trajectory. We also know the timing between it, so I can get all the information I need to fit that. Okay. So here's the calculation then. So for 13.9 feet and a basket of 8, and his release was 8.35 feet. That's the release height that he let it go. The flight of the ball when video recorded by the student. You got all these clips, and this is the data. Each black one, I hit this data point with the basketball. Here, more data, and a little bit of error, and then we fit those points with a full model, full 4-force model, and this is the fit I get. And you see it's pretty good. One of the things is the launch angle is 48.1 degrees, launch velocity 23 feet per second, and I'm using a coefficient for the basketball 0.3. Now, a coefficient of a basketball is not known either. That's the drag coefficient. Again, from a little bit of the work done in the literature, they claim it's somewhere between 0.25 and 0.5. So again, I've kind of got a number in the middle. And if I fiddle around with this, I can also get a fit with this dash line, where a CD of 0.5 and a 47.83 degree launch angle, like it's pretty comma there should be a decimal point, and at 22.38 feet per second. So that's pretty close. So what do those numbers mean? What the rule, what we're going to say here is to get the optimum place to fit this, you want to pick a initial velocity, launch velocity, at the minimum of all the velocities that you can choose to make a basket at the center, to put the basketball right through the center of the rim of the hole. This curve right here, that's doing the calculation for just gravity. You do the calculation for the full force model, including the drag, you have to increase the launch velocity a little bit. but all these angles more or less follow. So let's see how our player did. All right. So if you look at his velocity and his angle, he was at 48 degrees, and that puts him right here. And his speed, they go back there, his speed was about 22 and a half, 23 feet per second. Go back to the curve here, and you'll see that's just about where the minimum is. So he is right on target, all right, to have the largest margin of error and make it. Now, I haven't proved that yet, but if you look at this figure here, I've taken this out of the literature at a paper at American Journal of Physics, and you see what have you got here? To hit nothing but net, all you have to do is get your launch velocity and your launch angle in between these two full lines. What's colored in orange here? If you shoot the ball in that region where you can match the speed, launch velocity, and the angle, you will make nothing but net. If you're up in this region here, if you're off a little bit, you're not going to make it. You're going to hit the rim. As you go towards a higher and higher arch, all right, larger and larger angle, launch angle, you see you got a fairly constant region of error between the angle and the velocity. The minimum, which is right here, is the best. You can see where my free throw shooter shot it. He's right in the middle here. So he has you have the largest margin of error in angle and almost the largest margin of error in velocity. And still, the velocity's got to be right on. You got to be really good at getting your velocity right. And you get a little bit more leeway in terms of angle. I mentioned over here at 45 degrees, you got a very little leeway, 2 inches on each side, but at 60 degrees, you get 3.5 inches. Nobody shoots higher than 60 degrees. Steve Curry shoots around 58 degrees. So he likes to have the largest available width on each side, but he has to have a larger velocity. But he is not at the minimum. Now you can calculate this curve for each distance from the basket and for each release point. So every distance from the basket and every release point has its own curve. Okay. Try to finish up here in terms of our time. Now this is a plot of the margin of error for different height players shooting a free throw. This is the release height. So if you're very short, you should be shooting at 52.5 degrees. This is your margin of error in velocities. All right, and this is your margin of error in angle. So if you're short, let's see how you do compared to a 7-foot player. His margin of error is in 8 degrees, so he can be within 8 degrees of the minimum and still make the basket, while the short player only got 5 degrees. All right. So a taller player should be able to should do better, as how I want to say it, statistically have a more accurate free throw or even a three-pointer than a shorter player. This is the trend for different height players: a 5.5-foot player, a 6-foot player, 6.5, 7-foot player. The above launch angles at the given release heights give you the slowest moving ball at the rim. So that's the criteria. You get the slowest moving ball at the rim. Red Auerbach used to call that the lucky shot. How about Isaac McNeely shooting a 30-foot three-pointer? Let's take a look at this one against Syracuse. There it goes. All right, we track it down. A beautiful three-pointer. You see the beautiful parabolic arc. All right, can we fit that one? All right, there it is again. And here it is. He shot that ball at 31 feet from the basket at a release height of 8 feet from the floor, given his height and how long his arms are. And then I used the baseball model for the fitting lift coefficient and the CD coefficient of 0.4 for the basketball and the full forces, and I get this orange curve. It's not perfect. Now, I haven't tried really hard to fit it any better, but here's the basketball, the black dots of the basketball. Occasionally, I put a real basketball in there. And you can see my calculation. I don't don't quite go through the center, but you see from his shot, he went right through the center. Okay, so he made the shot, and he seems to be very good at. He doesn't hit the rim; he puts it right through the center. So I think his launch angle is 52 degrees. So that's pretty high, and you see he's got a very high speed as well, 34.8 feet per second. And I use 0.4 here. The optimum angle for the minimum energy is 49 degrees, but he opts for a higher angle. So the players have a choice between shooting for a larger target by using more arc and more speed, or going for a shooter's touch, which launches with less arc but a minimum speed. James Harden at 6'5" shoots at 49.6 degrees. That's a launch angle. It's for optimum for the slowest moving ball nears the rim. So if he hits the rim, he has a better chance of it going in. Stephen Curry does not. According to the data, Stephen Curry shoots at 58.1 degrees, like I've already mentioned. So he goes for a higher launch angle, a larger target area, but a higher velocity. Baseball data analytics is way ahead of other sports. Entire games and every movement is now video recorded with multiple cameras. There's a lot of work to do in basketball. In a sense, basketball is more set up for analytics than any sport because to get reliable data, because you play it inside without wind, without sun, and you have a very controlled environment. Women teams are now basketball teams are wearing devices that map their every movement throughout the game. So it's time to consider starting a movement to build a sports science lab at UVA to coordinate data analytics for all sports. As you know, we just built a new building for the data science department, and I've been in contact with them about a sports science lab, but there's a long ways to go. Thank you very much. Looks like I went over time a little bit, but I'll be glad to answer any questions and fill in any points that I've overlooked.
Great. Thank you, Professor Lindgren, for that incredible talk. I will tell you, I will never look at a basketball game the same, and I watch a lot of them. So this is perfect for March Madness. Everybody can bring their analytic mind. The bracket choosing is already over. But for next year, maybe you can cue in on a few players and put these well, sort of the methods to the test, so you will. So we're gonna go. Oh, go ahead.
I'm afraid as far as my course goes, I've had a lot of basketball players. There doesn't seem to be any coordination between their success in the class and their success on the court. It's almost inversely related.
That's unfortunate. But so we're going to get to our pre-submitted questions. And before we get there, if you have any questions you would like to ask, please type them in the Q&A box below. It is located next to the chat function. So let's go ahead and get started with that Q&A. So the first question I have is, how does the concept of conservation of momentum apply during a basketball game, especially in scenarios involving player collisions and ball transfers?
Well, conservation momentum is valid all the time. So if two players collide, yes, you have to conserve momentum, and even if there's a loss of energy, you still have conservation momentum. It's almost like when two football players collide, so they fall to the ground, and a lot of energy is lost. There's a lot of deformation going on, so that they hurt one another. You can break each other's bones. Your arms get twisted. There's a lot of heat generated, but overall energy is also conserved as well. But momentum is definitely conserved. Fortunately, however, the basketball does not have very much mass. So when a player throws a basketball to another player, yes, when he releases it, he does recoil back a little bit, but not much, because there's very little momentum carried by the basketball. And also in turn, when the other player catches it, he doesn't receive very much momentum either, because again, there's not much momentum carried by the ball. But in actual fact, it is conserved. You just don't notice it because there's not much carried by the ball. But you obviously notice when two players collide, because they're equally massive and one might knock down the other, which you see happen all the time.
Yeah. So our second question, and I'm sure people who are viewing right now would also want to know this. So, has Coach Bennett invited you to come work with his players? Like you said earlier, it's an inverse relationship. But has Coach Bennett ever invited you to work with his players to improve their free throw shooting or shooting in general?
Well, when I first started this course, it was advertised in the Department of Athletics, and it got around real quick. And he did contact me, actually, as well as the tennis coach and a few others. And I've met with them. I've met with the tennis people, and I did meet with Coach Bennett. He invited me to come to practice and watch it one day, and I did. This was several years ago, and we talked about data analytics. And he said, "Yeah, we have a camera up on the backboard for that reason." He says, "But we don't generally use it." And I had a couple of graphs with me, and we talked about it. I showed him the curves, and he had definitely had lots of interest. And but he said that when he tries to use such techniques with the players, they tend to forget what they've learned about that. And when they get into games, everybody's kind of uptight and nervous, and the excitement of the game is going on, and they tend to forget some of those small points.
Yeah, I mean, true. So we have a question from the audience. This goes back to baseball. How much does the humidity in the air, let's say at Fenway, in August, one of those really swampy days, as Eric says, affect the resistance to a fly ball or just a ball that's hit?
Well, that's a good question. Now, again, I would go back to the resistance. How much air? What is the density of the air? How much resistance more do you get when the density of the air is higher? That's how you will affect things. So you would have to know what that number is. Like in Denver, it's the density of the air is 18% less, and that makes it so. If it's 18%, that makes a difference of about 20 or 30 feet in a fly ball. All right. So like if the humidity is in the air is such that it amounts to about that much, it's going to be 20, 30 feet. It'll probably be about the same if again, the density is comparable. And in that case, it would be just the opposite, wouldn't it? It would be heavier. So so I guess I don't have a good answer, because in the case of the Denver case, it would be less, right? In this case here, it would be more. So I guess the way I would look at that is I think of it again, it would be more like a drag effect. Okay, it would be the drag coefficient, I would say, I think would be the better way to look at it, and that would be a little bit larger. But I can think of the drag coefficient be similar to the density. So if the drag coefficient is 18% larger or so, then that's going to make the ball go not as far. So it's like two different kinds of effects, right? One in case it's the drag effect, and the other case it's a density effect. So it's or a buoyancy effect. So anyway, so I would say that it would probably go 20 to 30 feet less, depending on what that number is.
We have one pre-submitted question that I think is an interesting one, so I want to ask it. If you could have dinner with any historical physicist and any famous athlete, who would they be, and why would you pair them?
Well, talking about professionals now, not amateurs, right?
That's right.
I can't think of any of my friends. Right? All right. So as far as physicist goes, I'd have to pick Richard Feynman. Not because he has the same first name, but because he's a very charming guy. I mean, he's a very smart guy, been an innovator. He's very versatile. He plays the drums, or the bongo drums. He used to hang out in Las Vegas, as a gambler. He sounds like a cool guy. So I would have to pair him up with another cool guy in sports, and I think that would be Roger Federer. I mean, Roger Federer is one of these, he's an expert at his craft. He's very friendly. He's always smiling, He's a charming guy. He likes to play tricks on the court as well. I mean, he likes to hit between his legs and do all these things. And so I think those two would get along quite well together.
I'm a huge Roger Federer fan, so that I would like to sit down with him as well. We got one question from the audience that I would like to pose to you, and that is, how does barometric pressure affect ball types in sports, especially in outdoor venues?
Okay, again, I'd have to resort to the density, right? Remember, all right, let's think about this. If the pressure goes up, the density goes up. The pressure goes down, the density goes down, right? And that density, that density factor, when you remember when I showed you those formulas, in the curve for the density, the curve for the drift coefficient, it was the drift coefficient times the density times the area, okay, times the velocity squared. That formula gave you the amount of force needed, right, that would hold the ball back. So if that density, if the barometric pressure goes up, that density goes up. So that means you would have a larger drag force acting on the ball. If the density goes down, that means you're going to have less. So in one case, if the pressure goes up, the ball is not going to go as far because the density went up. The pressure goes down, the density goes down. That means the ball will go correspondingly further. And that's pretty much the same kind of answer that has to do with the amount of water vapor in the air, because in effect it changes the density. So that's how I would answer that.
Then for our last question of the evening, I have to find a good one. So Randy from the audience asks, can you predict what the shot results will be if you have a stationary shooter shooting from the same location, assuming it's inside, not affected by weather?
No, can you, sorry, you could predict? Is that what you said?
Yep. Can you predict? Yep.
Yes, if you can predict it, if you know, let's do it this way. Let's say you get a radar gun and you got to measure, right? You got to determine how fast the ball is leaving from his hands, how high it's released from the floor. We call that the release height. So if you know how high the ball is off the floor, you measure that. Let's say you know how fast it's going to go. You determine that value of the launch velocity, okay? And you have to know the angle. So if you know the angle, you know the velocity of the ball, you know the height, and you know how far away you are from the basket. In my opinion, there's two more things you got to know: the drag coefficient for the basketball. And I'm saying that you don't quite know that yet. It's somewhere maybe 0.3, 0.4, 0.5 in that vicinity, but that can be determined by experiment, okay, for a given density of air, okay. And the other thing that you have to know is the lift coefficient. If you're going to you tend to put backspin on a basketball for stabilization, not necessarily to give you, more distance, although it does, but it's more like stables the ball so that it doesn't knuckle on you, because the seams can act like the stitches on a baseball and kind of let the ball dot back and forth as it flutters through the air. You tend to want it to rotate to balance those out, but you want it to rotate with backspin to give you the lift, all right, more arc, so that will give you more lift. And you got to know that coefficient. It's called the lift coefficient. It tends to be spin dependent as it's moving through the. So you got to know the spin you're going to put it on. You put on the ball, and you can measure that too. And this is done in baseball all the time. In baseball, there's been a lot of studies on this, but still, the data analytics is not good enough. And as I said earlier, it's harder to do in baseball because you got the wind blowing, and you got more variations in the atmosphere. But in a controlled environment, like a gymnasium for a basketball court, I think you will be able to do that. You just have to know all those factors. You know the force. There's the final four, the four forces. You know what they are.
So if everybody did their homework, we can we can all start
I claim that eventually you will be able to do that. You can almost do it now if you measure those quantities.
Well, thank you, everyone. It is 7:32. Thank you all for joining us, and thank you again, Professor Lindgren, for a fantastic talk on the physics of sports and your deep dive into basketball. We really appreciate it. And if anybody wants the recording will be out over the next few days. So be sure to share with anyone else who may find this interesting. But that is it for us tonight. Have a great night and a great weekend. If you want to learn more about UVA clubs, please scan the QR codes below. And I will mention that we'll be having our next Through the Lens on April 18th. That is a Thursday at 1 p.m. And that'll be with Professor Kathleen Shiro, who will give a talk about climate and weather. Thank you all for joining us. Have a great night.